And now our next speaker is Boris Lange from Edmund Optics, who will give us a talk about lenses, standard lenses, custom lenses, and is there something between? Boris, the stage is yours.
I assume that everyone can hear me. See smiling faces all over the board. Awesome. All right, short answer, yes. Any questions? No. Of course, I want to expand a little bit more on the topic as soon as I figure out how to, or which one of the instruments to use. This one is the right one. All right, so I want to briefly talk one slide, why do people use standard lenses? One slide, why do people care about fully customized lenses? And then we're going to talk in more detail about is there something in between, because we're going to see that there's quite a substantial difference in the approach whether you go for a standard and a fully customized lens. So why do people use standard lenses? Is anyone using standard lenses in the audience? Okay, that is far less people than I expected, I will admit that. So why do you use standard lenses? I guess because it's easy, right? That's the short answer. You have a wide selection of products on the market from a huge number of vendors, manufacturers. All the specifications are there, the pricing is there, the lead times are there, and there's no more variables left in your project, at least not related to the optics, maybe. So you save a lot of time, you save a lot of money, you don't have to think about many things in detail, you reduce your overall time to market, you have a simple life when you go with a standard optic. That's beautiful. So why do people at all care to use full custom lenses? Anyone in the audience who's ever used custom lenses? Okay, that means the difference doesn't use optics. I am concerned. Anyway, the point of full custom lenses is either you are looking for a specific performance that you don't get from the market. It's just not there because you are in a very specific niche with your application. The second thing is, though, you're really trying to optimize your cost-performance ratio of the optic you're using. So you're looking for some sort of a competitive advantage. Because at the end of the day, any off-the-shelf optic, any off-the-shelf lens you buy and use, it's a compromise. Somebody made design choices for you. Somebody made decisions for you. In what F number range does your lens perform well? In what waveband does your lens perform well? And also, in what working distance range does your lens perform well? Somebody made that decision for you, so if you don't need that much flexibility of that standard off-the-shelf lens, you may be overpaying for the optic that you actually need if you're trying to solve an application with just a narrow, specific set of parameters. Simple example, just the working distance. I'm not done with my questions. So who's familiar with MTF curves? OK, so short introduction to MTF curve. On the y-axis, you have contrast, right? I guess you're familiar with that, because that's what imaging is all about. So what contrast can you get in your image with a certain given optic at a certain given parameter set? Y is contrast, and X is resolution. So we start in the upper left corner at 100% contrast, at 0 line pairs per millimeter, which is to say that your object is infinitely far apart. And as you move on the x-axis to the right, you're bringing up your objects closer, closer, closer. And at some point, depending on how good your optic is, they will merge and blend together and blur together until they are indistinguishable. That's what you hit 0 contrast at. In that case, your line would go to the bottom. So that's what you see. They all start in the upper left corner at 100% contrast, and then you go down as you increase your resolution, which is what you expect, and I'm sure you also experienced already. So on the left side, we see all those curves for a working distance of 300 millimeters, and as we see, the optic performs quite well. It still hits like 20% contrast all across the board. The different colors, the different curves represent different positions in your image, in the center, in the corner, in between, just to make it short. The very same lens, you're now trying to use it at an infinite working distance, several meters away, or really like infinitely far away, like looking at the stars, for example. all of a sudden your MTF performance, well, maybe on axis the blue curve is still okay, it didn't change a lot maybe, but the rest looks quite different. So it has quite a different performance, and that might quite be an unpleasant surprise to you if you didn't check that before. So that was a long story short. Sometimes there's really value in narrowing down the specific parameter set to exactly what you need. And on this way to a full custom imaging optic, you will have to spend a lot of time. This is very rough numbers, and the devil's in the details. But just to derive a common understanding and finalize the specifications of what you need, you can easily spend 0 to 2 months. Doing optical design, optomechanical design, finalizing the design again is 3 months. And getting prototype is also around about 3 months. So in total, we're talking about a 6 to 8 month effort that includes design work, maybe weekly calls, get up to date what happened in the design process. Are we still on target? Did we run into issues? And it's a lot of fun, to be honest, to do it, but you got to have the time, and you also got to have the money, because of course you got to involve some amount of non-reoccurring engineering cost in the process, usually at least. But at the end of the day, at the end of this journey, you can be sure that you have the best possible product for your application, which does exactly what you need it to do and not more. And that might lead to that competitive edge on your system level. All right. So now I told you there's like standard products which essentially are on stock and you can have them today or tomorrow. And I told you you can also give us 6 to 8 months worth of time, and then we do exactly what you need. So it's a bit extreme, maybe. So it's a very valid question to ask, is there something in between? Just to, a few shortcuts. And of course there are. It depends on what you are exactly trying to do, of course. I've listed a number of possible changes and modifications that I've seen over the last years. For time reason, I'll just hit on 3 of those. The ones in bold, I'll just mention that it's very easy to customize an F number. It is also easy, I would argue, to make a lens more robust. You can glue optics and have also other certain techniques. You can save weight, depending on what exactly you're starting with, quite a lot. Very important for people who put imaging systems on drones. And you can also do things like changing the lens mount. But I want to expand a little bit more on the first 3 now, with the remaining time we have today here. So the first one would be, is it possible to integrate a filter? And that one is something we encounter quite a lot, especially with M12 lenses, because usually your C-mount lenses have filters, filter threads up front, and you can call, for example, this guy or ourselves, and we will be happy to provide you a filter that goes in front. For M12 lenses, however, there's nothing like this, and then you're stuck in this situation. Okay, how do I use this filter and this M12 lens? There's no thread. Do I glue it on top of each other? Do I put it between the camera and the lens? So in terms, if you want to make your life easier, there's of course always the option to just call your manufacturer and ask, can you please integrate the filter in my lens? And then we can have a look at the drawing of that lens, and if there's some space in between the optical elements where we can squeeze it in, that's a very nice way, a very nice solution. We can absolutely do that. A second aspect would be if you are more maybe in the life science world of things and you're looking at well plates, as I depicted it here. That kind of application lends itself to telecentric lenses, because you want to be able to look into each individual well by itself all the way to the bottom. So you need a telecentric lens to get that perfect 0-degree angular field of view and really get to the bottom of things, literally speaking. So, and now if you do a fluorescence analysis here, you need a very high-end filter to get rid of your laser excitation wavelength, and all of a sudden you realize, oh, it's getting quite a bit expensive all of a sudden if I want to put a big filter, high-end filter, in front of a telecentric lens. So here you might ask, okay, is it possible to also integrate that filter in the rear of the telecentric lens, where it will be smaller, and I can save a lot of money that way? And that's also, of course, something to discuss then, and usually we'll find space to make that happen for you. Also, the filter is protected in that sense, depending on your application, what you exactly do. Maybe you don't want a high-performing filter in the very front of your lens where it is exposed to your application, which might be a bit rough, dirty, spray water, I don't know. You tell me. But that's an easy thing to do. all in all, I'm summing up this first challenge. It's an easy task. You just require certain new custom metal parts that need to be designed. And of course, you need the filter. If it's a custom filter, then it gets complicated again because it's lead time and everything. But it's a very moderate amount of NRE that is involved. Of course, there's some amount of minimum order quantity there. And in terms of lead time, there's not too much of an impact when you compare it to a standard lens that you might buy off the shelf, because you only need to get custom metal parts in, and that's much easier and quicker than getting custom optics. Moving on to the second example, adjusting the working distance of a telecentric lens. So anyone using telecentric lenses? I mean, probably not, given the first responses. Anyway, they come at fixed magnifications, and you're supposed to use them at a certain defined working distance. And if you don't like the distance for various reasons, you want to make it shorter or larger, that's the question of how do you do that? So if you want to decrease it, it's very easy. You can just use spacers or distance rings like I depicted here. And I just pulled a random example of one of our telecentric lenses here. So say if you are just a little bit off with that working distance, you need to be a little bit closer than just something as simple as a 240 micrometer spacer would do the trick. You put it between your lens and the camera, and it gets you around about 11 millimeters worth of working distance, and you can move closer without changing the magnification too much in that example. You still might want to check MTF performance or things like relative illumination. That's a little bit more on the detailed side then again. But it's all in all an easy task, easy concept. If you want to go the other route and want to increase working distance, again, you immediately need custom metal, because you somehow need to remove the metal and get your optics closer to the camera, closer to the sensor. Same example with that lens. We start at 111 millimeter, but say you need to be a little bit further away because in your machine there's some things going on in between, and you just can't get up close to your object. Okay, just some different numbers to get you a little bit of a feel. If you were provided with a goal of achieving a working distance of 150 millimeters, that would translate into 890 microns that you have to move closer to your sensor with the optics. And so, yeah, you can of course remove it from your camera, maybe from your C-mount flange, or you can try to remove it from your lens, but it's not quite professional, I guess. So, yeah, rather, again, go down the route of getting some custom metal design done and have that telecentric lens modified for your needs. Last example, and I go back to the MTF curves I provided earlier today. So again, we start with that lens that performed well at 300 millimeters, but not so well at infinite working distances. Okay, so you go one level deeper, you look into the optical design of that lens, you see how it performs at infinite working distance again here in the MTF curve. And now you might ask yourself, okay, you've listened to me now for 10 minutes, you already might have seen that pattern of touching the optics, causes a lot of work, custom the metal. Quite all right. So you might ask yourself, how about we get some custom metal done and we just shift the optics around a little bit and see if we can get more performance at infinite working distance. That's essentially the idea. So you can see that that second element moved quite close up now. It's right in the middle now between the third and first element. And the question would be, yeah, can you actually improve your MTF performance with a simple mechanical change like this? The answer is, of course, it depends. It's a case-by-case call. You got to look into the details. And it's not even that first step, which is like a task that takes 10 minutes. Unfortunately, just because you improve your nominal MTF performance is not the end of the journey. You still have to do Monte Carlo simulations. You still have to do your yield analysis, because the nominal MTF curve isn't real. It's in a perfect world where there are no tolerances, there's no tips, no tilts, no decenters, every radius of curvature is perfect, every Abbe number is perfect, every index of refraction is perfect. So you got to dig deeper and do your yield analysis and really prove that this beautiful nominal MTF performance increase you saw also holds in production. So that's an extra task to do, and that's quite a lot of work actually, and that's actually almost as much work as designing from full scratch. Starting the design from scratch. Okay, so with that I'm almost done with my time, and I'd like to conclude. I already gave it away. If you just change the metal parts, that's most of the time an easy task to do, and you're much, much quicker than those 6 to 8 months. If you touch the glass, if you change anything around it, if you have to do the tolerance analysis again to see if your design yields well in manufacturing, then that's a much more severe change of your optic, and you need to expect a longer lead time for that design process. And again, I want to wrap up with who should care for a full custom. It's people that are very early in their project. It's people that really care a lot about their price-performance ratio, and this ratio outweighs the time and NRE constraints. So a few examples again, a few decisions that might drive you there. People who look for higher resolution that's not available on the market, or maybe you need a very exotic focal length. Maybe you need an athermal design. Maybe you have stray light concerns and nothing on the market really fits your needs there. Or you just want to lower your cost, actually. That's also absolutely possible by just narrowing down that parameter set that you're trying to solve. Maybe you look for specific magnification, or maybe you're interested in certain temperature behaviors. That's it. That's all I have. I thank you very much for your attention. My time is up. That's just the summary anyway. Thanks for showing up online, but especially also in person here at Vision Stuttgart. It was a pleasure to be here. If there are any questions, I'm happy to talk to you right now or over there at our booth. I don't recall the number, but we are right next to MTD, so you will find us. MTL. MTD. MTD.
Thank you very much. Thanks for the nice presentation. Are there questions concerning the approach, customization, possibilities?
Yeah.
Then I have a question.
Oh, no.
Can you recommend a cool tool to get these nice MTF curves, or is this Edmund Optics internal stuff? You are calculating these.
It is internal in the sense that you need either ZMax or Code 5, you have some specified optical design software in order to do that change. It's not a lot of work. So you can always call us, chat with us, send us an email and say, hi, here are my parameters, working distance, F number, waveband, sensor size I'm trying to use. And then it's like a 2-minute effort to get you that MTF curve. But it's not like something you can do it on your own. We have some MTF curves in our data sheets online on our website, but these are randomly picked parameters, which might or might not reflect what you're trying to do in your application. So if you're not happy with what you find there online, give us a call, contact us, and we're happy to send you like the specific data that you're looking for. I really recommend doing that, because MTF curves change a lot, as you've seen in that example between the 300 and infinite millimeter working distance. Extreme example, but still true, even on a smaller scale.
Okay, thank you.
Yeah, thanks.
Okay.
I stay on stage.